Hello, everyone. My name is Jingzhe, and I'm a PhD student at the University of Pittsburgh. In this video, I'm going to present our work titled CTDRB, Controllable Timed Data Release Using Blockchains. There will be 4 sections in this presentation, and I will start with background and motivation. Let me first introduce an interesting primitive called timed data release that protects sensitive data which can only be accessed until a predetermined amount of time passed. Also refers to sending data into the future. Here is an example. Let's say Bob has an important proposal that should be showed within a board meeting on Friday. However, this week he will be being busy and he cannot attend the meeting. But he still wants his proposal to be discussed during the meeting. So what should he do? He actually wants a service that can release his proposal on Friday. For achieving his objective, Bob can delegate his protection of the proposal to a timed release service provider. When the board meeting starts, the committee members can retrieve Bob's proposal from the provider. Even though Bob is not here, the committees can receive his proposal. There are some real-world applications naturally follow such a primitive. In secure voting system, we need to protect votes and make them only be accessible until the end of the polling process. Also, in a secure auction system, submitted biddings only can be revealed until all bids arrive. This work we consider to adopt the emerging Ethereum blockchain techniques to build a timed data release service. I will first introduce some preliminaries. So we consider the Ethereum account network, which consists of the following entities. The cryptocurrency flowed in over the network is called Ether, and there are 2 types of accounts over the network. The first one is called externally owned account, which is created by real-world users and can transfer Ether and invoke smart contract code. The second type of account is called contract account, which contains a piece of smart contract code. Ether transfer and smart contract code invocations are achieved in terms of issuing transactions. The entire network are transparent and tamper-proof. Let us see a general framework of the blockchain-based design, which is described as follows. A sender and a recipient first perform a negotiation for a new service, specifically prepare data and prescribed release time. And at the start time, the sender encrypts the data with a secret key, and he sends the encrypted data to a storage platform, and then splits the key into multiple secret shares, and recruits a group of trustees to protect the secret shares. So the shares are protected within the network before the release time, and at the release time, the recipient can receive the key shares, recover the original secret key, and extract the encrypted message from the storage platform. Finally, he can decrypt the message. The whole service will be enforced by a smart contract. Existing work mainly focuses on the following 2 aspects. The first line of work aims at constructing provable cryptographic scheme to perform data confidentiality protection. And the second line of work is to construct a practical protocol out of Ethereum blockchain to perform data confidentiality protection against different adversarial settings. However, existing effort only focuses on fully protecting the data confidentiality while significantly disregarding data control. The first limitation is that they cannot support data access control. So in the existing work, if the data is released after the release time, it becomes entirely public. And the second limitation is that they cannot offer data lifetime control. And in the existing work, before the release time, no one can perform temporary control over the protected data. So in this work, The problem is that how to realize data access control as well as data lifetime control while protecting data confidentiality in blockchain-based timed data release framework. So we solve the aforementioned problems by designing a systematic framework. And the first contribution is that we adopt a variant CPABE scheme to enable data access control. And based on the first contribution, a novel time token control service on the Ethereum blockchain is proposed to enable data lifetime control. And two practical data lifetime control primitives called data revocation and data release time modification are designed. So our framework heavily relies on a cryptographic scheme called TAFC to compare with the traditional CPABE scheme. In TAFC, the user will adopt the access structure to encrypt his data, and he can specify a release time, generate a time trapdoor and corresponding to the release time, and embed the generated trapdoor to a node in the access structure. When the time hits the release time, a time token will be released, and the time trapdoor can be exposed. So by jointly holding the time token and the satisfiable attribute set, one can decrypt the encrypted data. Such a scheme consists of the following algorithms, and I will detail them later. So there are also some other cryptographic preliminaries like hash function, digital signature, as well as the Shamir's secret share scheme are adopted in our framework. Here, I would like to formally describe our controllable primitives. So for the data access control, we aim at limiting the access scope of the data in a timed release service. For data lifetime control, the first one, we want to achieve data revocation, which allows the data sender to revoke the data at a time before the prescribed release time. For second one, primitive data release time modification, we allow the data sender to release the encrypted data at a time before the prescribed release time. At a high level, our design involves three proposed protocols. Concretely, Protocol 1, called Service Initialization, aims at enabling data access control. Protocol 2 and Protocol 3 together form the Time Token Control Service, T2CS for short, which provides the support for our data lifetime control. So let's first check Protocol 1. So we want to enable the data access control in this protocol. So the sender first prepares system parameters, and based on the attribute size of received from each recipient, generates a secret key by adopting the key generation algorithms, and privately transmit such keys to the recipient. We next start the design of time token control service. The first protocol, called T2CS setup protocol, has the following objectives. First, the senders will encrypt the original data by adopting the encryption scheme with a specified access structure. And here, the sender will adopt the token generation algorithm to generate a time token corresponding to a prescribed release time. And then he will provision the data lifetime control as follows. The sender first generates a public and private key pair and adopts the public key to encrypt the generated time token. And he will further split the private key CSK to multiple shares. And finally, the sender will privately transmit the secret share to the selected trustees. After T2CS setup, the timed data release normally starts. we next introduce T2CS enforcement protocol that supports data lifetime control. So this protocol aims at systematically supporting data revocation primitive as well as data release time modification primitive. So after sending the encrypted data CD and the encrypted time token to the IP to the storage platform, we want to achieve the data lifetime control in terms of temporarily controlling the encrypted time token stored in the platform, which is equivalent to temporarily control the release time of the shares held by the trustees. So we support data revocation in terms of designing a secret share proof of availability sub-protocol as well as the verifiable proof of deletion one. And also for data release time modification protocol primitive, we jointly adopt secret share proof of availability and modify secret share release sub-protocol. And the entire service will be monitored by our service auditing protocol. For the design of the secret share proofs of availability aims at helping sender to check the availability of the shares at any point of time before the release time. As an example, a sender can send the availability check request to each trustee. And after getting the hash of each share from the response from the trustees, us can verify the hash value by comparing them with the original ones privately stored by the sender himself, which finish the availability check in our framework. And to support the data revocation primitive, our approach is that after passing the proofs of availability, the sender requests each trustee to delete his held share. As an example, the sender first sends the request to each trustee, and as a response, each trustee transmits a deletion request, transmits a deletion response to the sender, which involves the signature signed by trustee's private key on the deleted share. After receiving the responses, the sender will publish all responses to the smart contract, which makes any misbehavior verifiable. This is also called the verifiable proof of deletion in our framework. Such a process will render the encrypted time token cannot be decrypted, which finally makes the protected data cannot be decrypted. Therefore, before the release time, the time is revoked by the data sender. So the second data lifetime control primitive is called data release time modification. So we realize this primitive in terms of informing all trustees the new release time, as well as notify all recipients the update. And at the new release time, we enforce the trustees to release secret shares to the smart contract. So after the new release time, any recipient, let's say R1, he can retrieve the secret share from the smart contract, recover the private key, CS key, and decrypt the encrypted time token using the CS key to get the original time token. And he can adopt the TFC's trapdoor exposure algorithms to generate a new ciphertext, and by providing his own secret key as well as the new ciphertext, he can perform decryption and get the original data. We also provide a service auditing protocol to capture misbehaviors. Like an example, we want to capture the cheating misbehavior in revocation primitive. So as an example, if any deleted share is shown after the revocation time, the following procedure can make it verifiable. Specifically, so any trustee can jointly hold the deletion evidence of the share on the public key of the responsible trustee, as well as the revoked share, to verify whether the trustee deletes the corresponding share properly. Next, we will show evaluations of our framework. So we implement the smart contract in Solidity, and we interact with the blockchain using the Brownie toolkit. The table shows the guest results regarding our implementation. We highlight that the data revocation scheme is related to the following 3 functions. And the data release time modification scheme consists of the following 5 functions. We also perform case studies to investigate gas consumption under different service scenarios. So we give an example here. So in this assumption, we assume that all the trustees honestly follow the T2CS service. The objective is to study the gas consumption of the 2 primitives when selecting different number of trustees. So we observe that the gas cost incurred by the 2 control primitives linearly increases with the growing number of selected trustees. So this one follows our protocol setting in the paper. So in this paper, we propose a controllable timed data release framework using blockchains, and which offers both data access control as well as data lifetime control while protecting the confidentiality of the data. So specifically, we adopt a variant CBB scheme to realize the data access control, and we carefully design a time token service to support the data lifetime control primitives. Finally, we implement a proof of concept prototype, and our case studies show that our data lifetime control primitives incur only a modest gas cost. Thanks.
Hello everyone, my name is Peyman Momeni. My co-authors are Sergey Gorbanov and Bohan Zhang. We are from the Cryptography, Security and Privacy Lab in University of Waterloo. And today I am presenting FairBlock on work on preventing blockchain front-running using identity-based encryption to CecureComm. So I'm going to start with defining the problem of front-running and MEV, and then I'm going to present cryptographic preliminaries of our work and then our design for FairBlock, and we sum up with evaluation and performance results, followed by future work and discussion. So what's MEV and front-running? MEV, or minor extractable value, and front-running strategies are one of the most notorious problems in blockchain space, specifically for smart contracts, such as decentralized exchanges, decentralized applications like voting mechanisms, and NFT marketplaces. And it is informally defined by the value other than transaction fees and block rewards, which can be extracted by reordering, censoring, and adding transaction in blocks, either by miners or validators or users. And blockchain front-running is a subset of MEV, which is the most popular subset of MEV, and it is defined by it's a family of strategies in which a malicious party manipulates the order of execution of transactions in a way that a transaction which is submitted later than an original transaction is actually executed earlier than the original transaction for financial profits mostly. And this, to make everything much more clear than the informal definitions, we have some scenarios here. The most popular approach is general front running. So in blockchains, transactions are mostly pending in a mempool and they're not executed. And normally a validator or miner will choose them and include them in a block and choose the order of execution of those transactions. These inclusion and ordering abilities of the miner or validators makes them in the alpha position of making some profits by ordering or censoring transactions. And they can either do it by themselves or collude with some users to extract profits. And this is normally done by the users by offering, essentially bribing miners with more transaction fees. For example, in this image in the left side, we have transaction 1, which is submitted earlier than other transactions to the mempool, but because the other transactions are offering more dollar signs, which is the transaction fees, the transaction 1 is only executed after the execution of all other 3 transactions. And this general front-running approach is actually used in many strategies these days. And the most popular approach in these days is sandwiching attacks. And this is the case that some user, Alice, is submitting a buy or sell order, for example, buying some kind of coin, and that coin is going up because the order is big, and evil bot, which is a malicious party, observes this juicy opportunity and puts the transaction just before the Alice's transaction and buys another amount of transaction, and these or the original transaction of Alice and the transaction of the evil bot will increase the price of that asset. And just after execution of these 2 transactions, the evil bot puts another transaction right after the original transaction and sells the asset. And this results in an almost guaranteed profit for the evil bot and some financial loss for the Alice user. And these MEV and front-running strategies has a lot of negative effects for blockchain applications. The most serious one is financial loss. They have more than 1 billion USD in loss for users and protocols. It is also resulting in high gas fees, consensus instability, because some miners sabotage the whole blockchain for some individual profit, and it also causes network congestion and wasted block space with all of the MEV transactions. Actually, 1 out of each 30 transactions in each Ethereum block is just submitted by MEV bots, which is wasting the very valuable block space of Ethereum. And now that we have explained the significance of MEV and front-running attacks, now I'm going to quickly summarize some of the front-running prevention approaches nowadays in industry and academia. The most popular name in the industry and academia is flashbots. Their basic idea is that instead of submitting transaction directly to public mempool, which is make it other bots can observe the transaction in clear and exploit the data. The idea is that you can submit them through a relayer to the miner directly, essentially back-channeling the whole process. Using this approach, other malicious parties cannot see the clear text data and exploit them. But the problem with this approach is the trust assumption in the relayer and whitelisted miners, because they can still see the clear text data, and they in fact are front-running transactions these days. The second approach, which is simple and has been implemented by some companies, is trusted execution environments such as Intel SGX. But the problem with this approach is the track of security breaches in Intel SGX and similar hardwares, and also it raises the bar for scalability because validators need to have a specific type of hardware, and it makes the user experience a little harder because of the significant latency. And another approach which is proposed is simple hashing, which is based on the classic commit reveal approach. So the idea is that you can hash your transaction, submit it somewhere. Once the order is finalized, you can reveal your transaction. So first you commit to your transaction, and then once everything is finalized, nothing can be changed. You will reveal the transaction, and everybody can take the hash of your transaction and see that the revealed transaction is actually the committed transaction. But the problem with this simple approach for most of the decentralized application is that the user can arbitrarily decide to not reveal the transaction and perform denial of service attacks. And based on this simple naive idea of commit reveal hashing, we have another commit reveal approach, which is to the extent of our knowledge, but the most promising approach, which is threshold decryption. In this work, we have FairBlock. We improve threshold decryption bandwidth overhead. So what's threshold decryption approach? The basic idea is that users can encrypt their transaction inside browsers, and they can sign that the encrypted transaction, and send it to somewhere, and consensus validators can include them in a block and finalize the order of the transaction. Once the order and inclusion of the transaction are finalized, a threshold committee named keepers can broadcast their decryption shares, and a relayer can, which is a designated individual, can combine these decryption shares and reconstruct the clear text of each of the transaction. And this prevents front-running and censorship attacks because nobody can see the contents of the transaction before finalization of the order and inclusion of them in the block. So nothing can be done when the transactions are decrypted. We have some kind of pre-execution privacy here. And the problem with this approach is that for each of the transactions, all of the validators should send their shares. So for N transaction and S validators, in the threshold decryption approach, we have N times S decryption shares, which is quadratic. But in our approach, we are going to show how to achieve it with just one share for each validators, which means for each block, we have all the validators just send a single share, and we have linear complexity. So, for example, for a decentralized exchange application, users encrypt their transaction with identity-based encryption in this approach, and they submit their transaction to a sequencer smart contract, and the sequencer smart contract preserves the ordering of the transactions. And once the order of transactions are fixed, our keepers in a network can send their block key shares, and a relayer can combine these block key shares to extract a single private key share, can decrypt all the transactions, and after decryption, the relayer submits them for execution to the target contract, which can be a decentralized exchange or any kind of a smart contract.
So let's introduce our cryptographic building blocks. The first one is identity-based encryption, which is the backbone of our work, and then we have distributed key generation. So identity-based encryption, originally proposed by Adi Shamir, is originally used for encrypting a message for a receiver without knowing the public key, and encrypting it for some email or some photo or some IP. And the receiver can talk with a third party and extract its private key to decrypt the message. So we have setup algorithm with lambda security parameter, which the output of this algorithm is master secret key and a master public key. And master secret key is used by the trusted third party. And a sender of the message can encrypt the message M for a receiver ID. The ID can be email address or anything else, and a master public key for the whole system. And once the encryption happens, we have the output ciphertext C, and the receiver of the message can authenticate himself to the trusted third party and extract the private key for that specific message, small d ID, which can be later used with a decrypted algorithm to decrypt the ciphertext C. And in this work, we have used distributed key generation to replace the trusted third party as a single point of failure with a decentralized committee of keepers, which are just validators. And these validators named keepers, they run the DKG protocol, for example, Peterson's DKG, to output a master public key and a master secret key shares, which all of them are remain the same through the whole process. And we just need to run the DKG process once, and very infrequently once the keeper set changes through this process. And in FairBlock, we have used smart contracts as the communication layer. So keepers and relayers deposit into the participant smart contract, and then, as I discussed, they use the DKG contract for master public key and making their shares of master secret key. And a user can read the master public key from a DKG smart contract and use the master public key and the ID of the block which its transaction should be executed in the future to encrypt its message. So let's take a magnifier on the encryption part. So as I said, we have identity-based encryption based on Bonner-Franklin. Other schemes can be also used, like Bonner-Boyens, to achieve better properties. So we have a symmetric bilinear pairing E hat, which maps G1s, groups G1s to GT, and the user can use the master public key and H, which is the ID of the block that the transaction should be executed, and message M, which includes the transaction information, and also the user sends a cryptographic hash function, cryptographic commitment using collision resistant hash function HC of its transactions, so the receiver of the message decryption can verify the correctness of the decryption algorithm later. So after the validators of the underlying blockchain finalize the order and inclusion of the encrypted transaction, keepers send their block key shares, and these block key shares does not leak anything about the master secret key shares. And this is where our work is good, because we don't need to run the DKG, because the master secret key shares remain secret. And then once the secret key shares are broadcasted, a relayer or group of relayers can use the block key and decrypt the transaction and then execute those. So block key extraction is simple, using the block key shares and Lagrange interpolation formula, just like the Bonner-Franklin scheme, and then we decrypt them and send them for execution to the target application, like a decentralized exchange. So our experiments show that actually our scheme for the threshold-based identity-based encryption is very feasible for today's application. For example, for 50 validators, it takes just 70 milliseconds for block key extraction, and encryption and decryption is negligible, because today's block time is, for example, for Ethereum is 15 seconds, and these times are actually very practical. So, and also we have experimented our approach and compared it to the threshold decryption approach, and we showed that for realistic scenarios we save the bandwidth overhead with 95% improvement or 99.6% in the first scenario, and which is very valuable. And we have compared our approach to the SGX, time block encryption, and threshold decryption. So the SGX approach, as I mentioned earlier, they have security and UX challenges, and time block encryption, which is based on a medium level difficulty cryptographic hardness problem, has a challenge between the trade-off against delay and security, and most of the times it is relying on some kind of specific hardware. As I mentioned, with FairBlock, we have improved the complexity from quadratic to linear for this application. And in the future, we are working closely for research and development with cross-chain protocols and layer 2 solution to solve the MEV problem with very same nature in these protocols. And also there is some interesting research works using multi-party computation and zero-knowledge proofs to prevent front running, but right now they have engineering challenge and scalability issues and latency issues then which is a very good space to improve these applications. And there's also the problem of blind front running and metadata front running, because you can basically front run users by just knowing sender's address. Because if someone is a good trader, you can just use the time of the trading information to front run them. In practice, you can. The idea is that we can use zero knowledge proofs to hide the sender's address by proving that the senders it has enough balance, but there is much more work to make it practical. Thank you very much, everyone, for listening to my presentation. I'll be more than happy to answer any kind of questions.
Hello, everyone. I'm Zhang Tianhe. I'm honored and proud to have the opportunity to speak at this meeting. Today, I would like to present my paper, Blockchain-Based Ciphertext Policy Hiding Access Control Scheme. I will use the following 4 parts to introduce: Introduction, System Model, Experiments, Conclusion. The first part is the introduction. As a promising encryption technique to ensure the security of shared data and to achieve flexible fine-grained access control. Ciphertext policy attribute-based encryption has drawn wide attention. However, most existing CTDRB access control schemes exhibit a single point of failure and privacy leakage. The main contributions of this paper are as follows. First, we propose an efficient attribute vector and policy vector generation algorithm. Second, we use the interplanetary file system to store ciphertext and store the ciphertext hash address on a blockchain using smart contracts. Third, the proposed scheme performs constant bilinear pairing operations during decryption. The second part is the system model. The model includes 5 entities: data owner, data user, consensus nodes, blockchain, and interplanetary file system. In this system, the access control workflow can be divided into a preparation phase and an execution phase. Preparation phase. First, the data user registers and consensus nodes generate relevant parameters and deploy the reversion contract. Data owner encrypts the plain text message according to the public key and access policy and stores the ciphertext on IPFS After that, data owner deploys the authorization contract and stores the ciphertext related information on the blockchain through transactions. Execution phase. First, the data user sends an access request to the data owner. After verifying the identity of the data user, the data owner sends the ciphertext related information to the data user. Finally, data user decrypts the ciphertext after performing the integrity check on the ciphertext. We propose an efficient attribute vector and policy vector generation algorithm using vector compression technology. Input given an attribute set and a policy set. Output a policy vector and an attribute vector. Then comes the smart contract design part. Revocation contract. This contract is deployed by consensus nodes and is responsible for managing users who have left or retired in the system. It mainly includes the following functions. First, update assert. Second, get assert. Authorization contract. This contract is deployed by data owner and is responsible for storing ciphertext related information. When data user sends an access request, it calls the revocation contract to check the identity of data user so as to determine whether to send ciphertext related information. It mainly includes the following functions. First, init storage. Second, judge. Our solution includes the following 6 algorithms, namely setup, key generation, encrypt, on-blockchain, decrypt, revocation. The third part is the experiments. In this section, we compare the proposal scheme with the proposal existing methods, which are shown in the table. We primarily compare the access revocation, type of heading, and other performance features. Comparative results show that the proposal scheme has certain advantages in different properties. We compare the PK, CT, and SK sets of these schemes. The table shows that the PK sets in literature 28 is the smallest, compared to literature 7 the proposed scheme achieves a shorter PK. The storage cost of literature 7 and the proposed scheme only depend on the number of wildcards in the access policy, which typically requires a smaller storage cost than literature 13, 10, 28, compared with literature 7. The size of PK, CT, and SK in the proposed scheme is markedly smaller. Therefore, the storage cost required by the proposed scheme is minimal. As shown in the table, the computational overheads of the schemes in literature 13, 10, 28 increase linearly with the number of attributes. The computational cost of literature 7 and the proposed scheme are only related to the number of wildcards. Typically, the number of wildcards will be much smaller than the number of attributes. During decryption, pairing operations in these schemes increase with the number of attributes or wildcards, resulting in high computational overhead for the decrypt algorithms. The proposed scheme has a constant number of pairing operations in the decryption phase and is thus more efficient based on the above analysis. The computational cost required by the proposed scheme is minimal. The picture on the left shows the comparison results of encryption time. It can be seen from the picture that the encryption time of the proposed scheme and the other three schemes increase linearly with the number of attributes. The efficiency of scheme literature 7 is the highest, but the efficiency of the proposed scheme is not much different from it. The picture on the right shows the compression results of decryption time, as can be seen from the figure. Compared with the schemes in literature 7, 10, 28, the computational overhead of the proposed scheme in the decryption phase doesn't change much with the increase of the number of attributes, and the efficiency is higher than the other three schemes. The main reason is that the scheme in this paper has a constant number of pairings in the decryption phase, so the efficiency is the highest. The last part is the conclusion part. In this paper, we presented a blockchain-based Ciphertext policy hiding access control scheme, which achieves distributed and reliable access control and ensures user privacy and security. Thanks for your time.